Today we want to parameterize curves in R3. The way we want to think about this is imagine a fly is buzzing around your room, if your room is in fact in 3 dimensions. If you have like a 2-dimensional relaxation room, then then it's different. So imagine a 3-dimensional classroom, the fly is buzzing around, and that fly's path is tracing out a collection of points in R3, and we want to describe it. And we're going to imagine describing it with a 3-dimensional Etch-a-Sketch, where we have one knob controlling horizontal movement, that's our X knob, and another knob controlling our vertical movement. So rather than having our vertical coordinate being a function of our horizontal coordinates, we're going to define them independently of each other, but relative to some parameter. So we can imagine the fly buzzing around the room, and it's moving left and right, up and down, forward and backward. And its position doesn't have to be, its height does not have to be a function of its position above the floor. Its left and right position above the floor does not have to be a function of its forward and backward position on the floor. It's just kind of flying around. Looks random. I don't know what flies are doing. I don't know what's in the mind of a fly. So we're just separating the 3 axes of movements, horizontal, vertical, and our Etch-a-Sketch has to be 3D, so we'll have a third knob that moves the stylus out of the screen and then back down towards the screen and then behind the screen. You can't see it on the video, but I'm pointing underneath the table. Right. So we're going to define a collection of points in R3 with 3 different functions. The X, Y, and Z coordinates will all be 3 separate equations. So there's some X function controlling our forward and backward, some Y function controlling our left and right, and some Z function controlling our up and down. Any questions? All right. So if we think back to looking at parameterized curves in Calc 1, we were doing the same thing. We just had z of t was equal to 0. In Calc 1, we had x of t, x of t, y of t, and we were describing motion in a plane that way. And then z of t was just equal to 0 back in Calc 1, because we didn't have any up or down. We were working in 2 dimensions. We were all being limited like this. But there was that third dimension that we can imagine. So we have describing a curve x of t, y of t as it runs around the piece of paper. But what if all we have now is a third coordinate, where now instead of just running around stuck to the piece of paper, we can lift our pen up off of the paper and draw in space. Then it becomes like one of those Disney commercials where people like all trace out the ears, but it's in 3D. So you can see their fingers moving backwards and forwards. All right. Let's imagine our favorite example. Back in motion, describing a curve in a plane. So the unit circle is described as cosine of t and sine of t. We're just saying x of t is cosine of t, y of t is sine of t. So cosine of t for t between 0 and 2 pi. So set the Wayback Machine to Calc 1 and also back to trigonometry. So our cosine is going to, when t is equal to 0, we have the point 1, 0. When t is equal to pi over 6, then we'll have root 3 over 2 and a half. So what's going to happen is the x-coordinate is going to start off at 1, drop down to -1, and then come back up to 1. While the x-coordinate is going down and back up again, the y-coordinate is going to start off at 0 and go up to 1, back down to 0, down to -1, and then back up to 1. And then when we put those two things together, that will form a circle going around counterclockwise 1 time. So the x of t starts off at 1, and the x-coordinates drop down to -1 and then go back up to 1. So it starts off at 1, goes down through 0, goes down to -1, and then back up to 1. The y-coordinates, while it's doing this, we start here and we're going this direction. We'll start off at 0, go up to 1, go down to 0, down to -1, and then back up to 0. So sine of t is going up, down, and up again. So the y-coordinate goes up, down, and up again, while the x-coordinate goes down and then back up again. All we're going to do now is put a z-coordinate. So while the x goes down and then up, and then the y goes up, down, then up again, we could just have the z-coordinate do something else. Our favorite thing to do is just to take the unit circle and expand it into a helix. So let's do that. This is our usual first example in calc books when we get to this point. Like I've written a calc book. So what we're going to do now in R3, we're going to stretch the unit circle into a helix for a new example. So what we're going to do is we're going to say cosine of t, sine of t. That's going to make a circle. The x is going to go down and then back up again, while the y is going up, down, up again. And that's going to make a circle if we look at it from the top. But then I'm going to say z is just going to be the t coordinate. And this is where we're going to separate things at 0 and 2 pi. And we're going to grab that point and we're going to pull it up so that when t is equal to 2 pi, we're back at the starting point, but 2 pi units up. So we made like a spiral staircase. So we're going to start here. We're going to start at 1, 0, 0. From the top, it's going to the x is going to go down and then back up again, while the y goes up, down, and then up again. But while that's happening, instead of just confining this all to the xy plane, it's going to go up as we go around. And it's going to wrap around 1 time. So we're going to end up here at the point 1, 0, 2 pi. And that'll be directly above 1, 0, 0. So we start at 1, 0, 0 when t is equal to 0. We end up at 1, 0, 2 pi when t is equal to 2 pi. In the middle, I don't need a pencil for this. We imagine halfway up. That's when we'll be at the back end. That'll be the point -1, -1, 0, and pi. If we're a quarter of the way up, that'll be, we've gone around here, so that'll be at 0, 1, and pi over 2. And then if we're 3/4 of the way up, it'll be hard to see. I can't draw it. So I'm going to be at 0, -1, pi. I don't think I drew that right. Nope, I can't draw it. So if we view it from the top, if we view things from the top, we imagine this point going around the circle, but as it does so, comes out of the paper. So as the point goes around this circle, the point is coming out of the paper. If we look at it from the side, so if the x-axis is coming right out, straight out at us, and we're looking at the y-axis from the side, and then the z-axis comes out, then on the y-axis, we're going to see a sine curve, as the y is going to go, we're not going to see the forward and backwards motion, but it's going to start off 1 unit up here, and the y is going to go up, down, and up again. So it's going to look like a sine from the positive x-axis. From the positive y-axis, we're going to see a cosine. So if I take this and turn it to the side, so that the positive y-axis, we're going to stand here and look back at the curve. Our x-axis, it'll be turned this way, and our z-axis will be going up and down like before. And we'll see our x start off at 1, drop down to -1, and go back up to 1. So there's our view from the positive z-axis, from the positive x-axis, and from the positive y-axis. And all we're doing is building a spiral staircase. Any questions? All right. Yeah, I can't even picture it anymore. So the point, ignoring my terrible attempts at drawing an example of a curve in R3, the point is that we need some way to describe a set of points in R3 that is one-dimensional. I need to be able to describe a path, a one-dimensional curve running through R3. If I try to describe z as a function of x and y, or any permutation, like y is a function of x and z, or x is a function of y and z, I'm going to end up with a two-dimensional surface in R3. So if we have an equation that relates x and y and z, we're going to get a surface in R3. So now we need a way to describe a one-dimensional curve in R3. And the way that we do that is to parameterize the coordinates. All right, so let's pause the video here and talk about next steps.